Two spacecraft leave the solar system on the same day. The first is a machine we already know how to build. A probe with a mass measured in hundreds of kilograms, pushed outward by rockets and planetary gravity assists. Once it is clear of the Sun, it coasts at about the speed of Voyager 1. Give it a perfectly straight path and an engine that never fails, and it will need roughly 18,000 years to cross 1 light-year. The second spacecraft is almost nothing. A chip, a camera, a radio or laser, and a reflective sail with a total mass of only a few grams. It carries no fuel. For a few violent minutes, a colossal array of lasers pushes it from behind. If the idea works as proposed, it could cross the same light year in about 5 years. 18,000 years and 5 years. The same distance, the same universe, the same speed limit. No wormholes, no suspended animation, no new laws of physics. That difference exposes the argument hidden inside nearly every discussion of interstellar travel. 1 light-year is often described as a wall, as though space itself becomes forbidden beyond some invisible frontier. The opposite story is just as common. Technology always improves, so a better engine will eventually make the stars accessible. Both claims are too simple. A light-year is not a wall against all matter. It is a filter. It treats a gram differently from 1,000 tons. It treats a flyby differently from an arrival. It treats a photograph differently from a living crew. And it treats a spacecraft that only has to accelerate very differently from one that must also slow down. The uncomfortable conclusion is that crossing the distance may be the easiest part of the mission. The harder question is what must still be functioning when the crossing ends. A light year is the distance light travels through vacuum in 1 Julian year, a year of exactly 365.25 days. Because the speed of light is fixed at 299,792,458 meters per second. That distance is about 9.46 trillion kilometers. The number is familiar enough to feel harmless. It appears in school books, planetarium displays, and documentaries as a convenient unit. 1 step above the astronomical unit and 1 step below the parsec. Yet the familiarity hides the scale. Light could circle Earth more than 7 times in a second. It reaches the Moon in about 1.3 seconds. It takes a little over 8 minutes to travel from the Sun to Earth. Then it continues for another 364 days, 23 hours, and almost 52 minutes before completing a single light year. The average Earth-Moon distance fits inside 1 light year about 24.5 million times. The average Earth-Sun distance, 1 astronomical unit, fits inside it more than 63,000 times. Neptune orbits at roughly 30 astronomical units. Even the architecture of the planetary system, which feels enormous when measured by human voyages, occupies only a small fraction of the distance under discussion. But scale alone does not explain the difficulty. Empty distance is not automatically hostile. A road can be long and still easy if fuel, repairs, and communication are available along it. Interstellar space offers almost none of those conveniences. The local interstellar medium is extraordinarily thin, often containing only a fraction of an atom to a few atoms in each cubic centimeter, depending on the region. It is not perfectly empty. It contains hydrogen, helium, heavier ions, magnetic fields, cosmic rays, and dust. At low speed, that material is almost irrelevant. At a large fraction of light speed, the same sparse medium becomes a beam of energetic particles, striking the spacecraft head-on. That reversal matters. The emptiness that removes drag also removes easy braking. The emptiness that looks safe at ordinary speeds becomes radiation at relativistic speeds. The emptiness that provides a clear path also gives a damaged spacecraft nowhere to stop and no nearby workshop from which help can be sent. To see why the mission definition matters, begin with Voyager 1. Launched in 1977, it used Jupiter and Saturn to gain speed and eventually crossed the heliopause, the outer boundary of the Sun's particle-dominated bubble. It is the most distant human-made object and is escaping at roughly 3.5 astronomical units per year. That is a magnificent achievement. It is also only about 1/18,000th of a light-year per year. After nearly half a century of flight, Voyager has covered only a few thousandths of 1 light-year. It is already so distant that a radio message takes more than 23 hours to reach it. Engineers send a command, wait almost 2 days for the round trip, and hope that an aging machine built when many of its operators were not yet born has understood. Voyager reveals one version of the light-year problem. Patience cannot repair hardware forever. A journey of 18,000 years is not merely long. It changes the category of the object that must survive it. No electronic system has operated for that length of time. No human institution has maintained a technical project for that length of time. Languages change, nations disappear, coastlines move, and climates reorganize. Even if the probe were physically capable of coasting for millennia, the civilization listening for it would have to preserve the knowledge, equipment, and intention required to recognize its signal. It is tempting to escape this conclusion by pointing to the fastest spacecraft ever built. Parker Solar Probe has moved at about 192 kilometers per second during its closest passes by the Sun, more than 10 times Voyager's outward speed. If that velocity could be carried unchanged into interstellar space, 1 light-year would take roughly 1,600 years rather than 18,000. That sounds like progress until the conditions are examined. Parker does not obtain that speed from an engine that could drive a starship. It falls deep into the Sun's gravitational well. Its record velocity occurs near perihelion, where the Sun's gravity has converted potential energy into speed. As the probe climbs away, it slows again. The record is real, but it is not a cruise capability. It demonstrates how fast a spacecraft can move in a particular orbit, not how fast humanity can launch useful payloads into the dark between stars. This distinction between peak speed and sustained mission speed is one of the first places popular accounts go wrong. Another is the habit of treating travel time as the only variable. At 10% of light speed, the arithmetic is easy. 1 light-year takes about 10 years in Earth's frame. At 20%, about 5 years. At half the speed of light, about 2 years. The numbers create the impression that the problem has been solved once a velocity has been named. But a velocity is not a propulsion system. It is not an energy source, a heat radiator, a shield, a navigation method, a communication link, or a brake. It does not explain how the spacecraft reaches that speed, how much mass survives the acceleration, or what happens when the destination arrives at tens of thousands of kilometers per second. A bullet can cross a room quickly. That does not make it a passenger vehicle. The central mistake is to confuse motion with transportation. Transportation means more than passing through a coordinate. It means moving something useful while preserving its usefulness. For an interstellar probe, that may mean keeping sensors aligned, storing power for decades, surviving dust impacts, taking measurements during a brief encounter and sending a detectable signal home. For a crewed vessel, it means all of that plus air, water, food, radiation protection, medical care, mechanical redundancy, psychological stability, and a habitat that does not slowly poison its occupants. If the mission is supposed to orbit a planet, land, or return, it must also lose almost all of the speed that made the journey tolerable. Once those requirements are included, the light year stops behaving like a simple distance. It becomes a systems problem in which every solution increases another cost. Add shielding, and mass rises. More mass requires more energy. A larger power system produces more waste heat. Larger radiators add more mass and more area for dust to strike. Add redundancy, and the payload grows again. Add propellant for braking, and that braking propellant must itself be accelerated during departure. Add a crew, and the ship becomes not merely a vehicle, but an artificial biosphere expected to remain stable farther from help than anything humans have ever built. This is why the strongest argument against calling one light year an absolute wall is also the argument that clarifies what the wall really is. We may be able to send very small machines across it. The physics of a gram-scale flyby is far kinder than the physics of a settlement ship. If that is accepted, then the question changes. Not, can anything cross 1 light year? Something probably can, using known principles and technologies that are difficult but not magical. The sharper question is, how much capability can cross? How quickly, and in what condition will it arrive? That question begins with the oldest law haunting every rocket. Whatever a spacecraft carries must usually be accelerated along with it. The rocket equation is often introduced as a formula about fuel. In practice, it is a formula about consequence. A rocket moves by throwing mass backward. The faster that exhaust leaves, and the more propellant the vehicle carries relative to its final dry mass, the larger the change in velocity the rocket can achieve. The relationship is logarithmic. That single mathematical detail is why ordinary intuition fails. If a car needs to go twice as far, it may need roughly twice as much fuel. A rocket cannot be scaled so casually because it must accelerate the fuel it has not yet burned. Extra propellant adds capacity, but it also adds mass. More mass demands still more propellant, which adds still more mass. The vehicle begins to carry fuel for the purpose of carrying fuel. For a hydrogen-oxygen chemical engine, an effective exhaust velocity of a little more than 4 kilometers per second is close to the practical high end. That is excellent for climbing out of Earth's gravity and crossing the solar system. It is almost useless beside a target velocity measured in thousands or tens of thousands of kilometers per second. Consider a simplified ideal rocket with an exhaust velocity of 4.4 kilometers per second. To gain 10 kilometers per second of velocity, it needs an initial to final mass ratio of roughly 10. That is demanding but familiar. To gain 20 kilometers per second, the ratio approaches 100. To gain 40, it rises to several thousand. At 100 kilometers per second, still only about 1/30th of 1% of light speed, the ideal mass ratio reaches billions. These figures do not describe a practical vehicle. They deliberately ignore tanks, engines, staging losses, guidance, structural margins, and the need to slow down. Their purpose is more severe. Even the idealized case collapses before reaching interstellar speed. Engineering improvements cannot rescue a propulsion method when the exponent has already become absurd. This does not make chemical rockets primitive or failed. It defines their domain. Chemical propulsion produces high thrust, can lift vehicles from planets, and has carried every human who has traveled beyond the atmosphere. It can send probes to Mars, Jupiter, Pluto, and escape trajectories. Calling it inadequate for a light year is like calling a ship inadequate for reaching the moon. The machine is not bad. The environment has changed. Nuclear thermal propulsion improves the situation without changing its structure. Instead of burning fuel with an oxidizer, a reactor heats a lightweight propellant, usually hydrogen, and expels it through a nozzle. The rover and NERVA programs in the 20th century built and ground-tested nuclear rocket reactors. Their performance demonstrated specific impulses around twice those of the best chemical engines, corresponding to effective exhaust velocities near 9 kilometers per second. For missions to Mars, that improvement is profound. It can reduce propellant requirements, shorten travel time, or increase payload. For interstellar flight, doubling the exhaust velocity only halves an exponent that is far too large. A nuclear thermal engine remains a rocket carrying reaction mass, and the temperature of its reactor limits how fast that mass can leave. Materials must survive the heat. The exhaust cannot be made arbitrarily energetic without destroying the engine that contains it. Electric propulsion takes a different bargain. Ion and Hall thrusters accelerate charged particles to exhaust velocities far beyond chemical rockets. They use propellant efficiently, but their thrust is low because available electrical power is limited. A spacecraft can accelerate gently for months or years, building speed that a brief chemical burn could not provide. This has transformed many deep space mission designs. Yet interstellar ambition exposes the power problem. High exhaust velocity is valuable only if enough mass can be expelled quickly enough to push the spacecraft. A thruster that is exceptionally efficient but produces a fraction of a Newton may take years to change the velocity of a modest probe. Increase the electrical power, and the reactor, generator, conversion equipment, cabling, and radiators grow. The engine becomes lighter on propellant and heavier on machinery. A nuclear electric spacecraft might plausibly reach hundreds of kilometers per second under aggressive assumptions. At 200 kilometers per second, 1 light year still takes about 1,500 years. That is astonishingly fast beside Voyager and unusably slow beside a human lifetime. Again, the technology has not failed. It has reached the edge of the mission class for which it makes sense. This is the point where discussions often leap to nuclear pulse propulsion, because nuclear explosions release energy at densities chemical reactions cannot approach. Project Orion, studied during the late 1950s and early 1960s, proposed detonating nuclear pulse units behind a massive pusher plate. Each explosion would deliver momentum to the plate. Shock absorbers would smooth the sequence into an average acceleration the vehicle could survive. The concept sounds like a refusal to engineer delicately, yet it was examined by serious physicists and weapons designers using known mechanics. Small tests with conventional explosives showed that a model vehicle could ride repeated pulses. The attraction was not elegance, it was scale. A pulse vehicle could, in principle, accelerate very large payloads with thrust far beyond electric propulsion. For the solar system, versions of Orion promised enormous cargo capacity. For interstellar missions, later extrapolation suggested that highly optimized thermonuclear pulse systems might reach a few percent of light speed. At 3%, 1 light year takes a little over 33 years. At 5%, about 20. For the first time, The journey fits inside a working human life. But those numbers are not a demonstrated performance specification. They are the far edge of concept studies built on nuclear devices, pulse shapes, materials, and vehicle scales that were never tested as an integrated system. A pusher plate would have to survive thousands of nearby explosions. Pulse units would need to be manufactured, stored, and fired with extraordinary reliability. The ship would carry a nuclear arsenal as propellant. Launch and testing would create political, legal, environmental, and security problems unlike those of any normal space program. The deeper penalty appears when the mission is required to arrive rather than merely pass a line in space. An Orion-like craft that accelerates to 5% of light speed has accumulated enormous kinetic energy. To stop, it must perform an equivalent sequence in reverse. Unless a braking system already exists at the destination, the ship must carry the pulse units needed for deceleration from the beginning. Those units are dead mass during acceleration, so more departure propellant is required to accelerate the braking propellant. The mass spiral returns. A flyby can spend nearly all of its mass budget on departure. An arriving mission cannot. Fusion propulsion offers the same promise in a more controlled form. Fusion combines light nuclei and can release far more energy per unit mass than chemical reactions. Some fusion products are charged particles, which in principle can be directed by magnetic fields to form an exhaust with velocities of thousands or even tens of thousands of kilometers per second. The most famous detailed study is Project Daedalus, conducted by the British Interplanetary Society in the 1970s. Daedalus was an uncrewed two-stage probe intended to reach Barnard's star, almost 6 light-years away, in about 50 years. It would ignite pellets of deuterium and helium-3 in rapid succession, using the fusion plasma as exhaust. The design's cruise speed was about 12% of light speed. That velocity would cross 1 light-year in a little over 8 years. It is genuinely interstellar. It also required a vehicle with an initial mass of roughly 54,000 tons, most of it propellant, to deliver a scientific payload of a few hundred tons. The design did not include stopping at Barnard's star. It was a fast flyby, because adding full deceleration would have transformed an already gigantic vehicle. Daedalus remains important precisely because it was not a casual sketch. Its designers tried to account for staging, pellet injection, ignition, magnetic nozzles, structural mass, erosion shielding, navigation, and communications. The result was not proof that such a probe could be built. It was a map of what a physically coherent attempt might demand. That map is sobering. The required fusion fuel included helium-3 in quantities not available on Earth. The study imagined obtaining it from the atmosphere of Jupiter, which means that the supply chain for the star probe would begin with industrial operations around a gas giant. Before launching the interstellar machine, a civilization would need mining systems, separation plants, tankers, orbital construction yards, and a fusion engine capable of firing millions or billions of pellets without catastrophic failure. Modern fusion research has advanced far beyond the 1970s, but the distinction between a laboratory event and a Starship engine remains immense. The National Ignition Facility has repeatedly produced fusion yields greater than the laser energy delivered to the target, a historic scientific achievement. That is not the same as generating net electricity for a power grid, because the entire facility consumes much more energy than reaches the target. It is still farther from a compact engine that must ignite pellets many times per second, direct the products into thrust, reject waste heat, and operate for years without maintenance. A fusion starship is not ruled out by a known law. That makes it more interesting than a fantasy. It also makes careless optimism more dangerous. The physics is real. The machine is not. The strongest technological counterargument now comes into focus. Rockets are punished because they carry the energy source and often the reaction mass they need. What if the energy source remains at home? Photons have no rest mass, but they carry momentum. When light reflects from a surface, it transfers a tiny push. Sunlight already does this to every object in space. Solar sails turn that pressure into propulsion by presenting a large reflective area with very little mass. A laser sail intensifies the idea. Instead of depending on sunlight spreading in every direction, a phased array concentrates an enormous beam on a small sail. The power plant, generators, cooling systems, and most of the mass remain near Earth. The spacecraft does not accelerate its own fuel because it carries almost none. This architecture escapes the ordinary rocket equation during the acceleration phase. It does not escape physics. It simply moves much of the difficulty off the vehicle and into the infrastructure behind it. Breakthrough Starshot is the clearest modern example. The program studies whether a ground or space-based laser array in roughly the 100-gigawatt class could accelerate gram-scale spacecraft attached to meter-scale sails to around 20% of light speed. At that velocity, Alpha Centauri could be reached in a little more than 20 years, and 1 light-year would pass in 5. No statement in the original argument survives contact with this proposal unchanged. 1 light-year cannot be an absolute barrier if a concept using known photon momentum can cross it within the lifetime of a research team. The laser sail is therefore not a footnote. It is the best objection to the claim that the distance itself is impossible. A careful analysis has to grant the objection its full strength. The underlying physics is established. Radiation pressure is real. Phased arrays are real. Thin films and photonic structures are real. Integrated cameras, processors, sensors, and communication devices can be made extraordinarily small. The spacecraft does not need food, air, or a comfortable acceleration. It may endure thousands of times Earth's gravity because a chip has no bones, blood vessels, or organs. Mass production could allow many probes to be launched, accepting that some will fail. This is exactly how difficult frontiers often open. Not with a full-scale human expedition, but with instruments small enough to tolerate conditions a crew cannot. The first object to cross 1 light-year quickly may not resemble a ship. It may resemble a piece of patterned film with a computer attached. That possibility should make anyone cautious about using the word impossible. It should not make anyone careless about the word mission. A Starshot-like probe must first survive acceleration. A beamer near 100 gigawatts is not simply a very large laser. Its many emitters must act as one optical instrument. Their phases must remain coordinated with precision much smaller than the wavelength of the light. The array may span kilometers. Atmospheric turbulence, vibration, thermal expansion, and microscopic timing errors distort the wavefront. Adaptive optics would need to correct those changes fast enough to keep the beam centered on a sail racing away from Earth. The sail faces a different extremity. It must be extremely reflective because absorbed laser energy becomes heat. Even a tiny absorption fraction matters when the incident beam carries power comparable to the output of a large nation. At the same time, the sail must be thin and light. A perfect mirror that weighs a ton will accelerate poorly. A nearly weightless film that absorbs too much will melt. Materials researchers study nanophotonic structures that combine low absorption in the laser band with strong thermal emission at longer wavelengths. The desired object must reflect the driving light, radiate heat, remain mechanically stable, and preserve its shape under enormous acceleration. Each requirement can be stated in a sentence. Satisfying all of them in a meter-scale sail at once is the problem. Beam riding stability is equally unforgiving. A sail that tilts may redirect the force in a way that increases the tilt rather than correcting it. A beam that strikes off center may push the craft farther from the center. Some sail shapes and optical patterns can create restoring forces, and laboratory work has begun to explore them. Yet the full regime involves flexible structures, intense power, rapid acceleration, and changing wavelength in the sail's frame as its speed rises. The spacecraft must also be launched into the beam with exquisite alignment. During a few minutes of acceleration, it travels millions of kilometers. A tiny angular error at departure becomes an astronomical miss years later. There is no pilot correcting the trajectory from Earth in real time. By the time a problem is seen, the relevant event has already happened. After the beam switches off, the probe becomes a projectile coasting at 60,000 kilometers per second. It cannot phone home for new fuel. It cannot unfold a spare antenna the size of a house. Its power system must remain viable through years or decades of darkness. Its electronics must tolerate radiation. Its clock and navigation solution must remain accurate enough to point a camera during an encounter that may last hours or only minutes for the most valuable close observations. Then the interstellar medium arrives. At ordinary spacecraft speeds, a hydrogen atom drifting through space is harmless. At 20% of light speed, it strikes with energy in the mega-electron volt range. Heavy ions are rarer but more damaging. Dust grains carry vastly more mass than individual atoms. Models disagree about the exact distribution of grain sizes along a specific route, and that uncertainty matters. A probe with a tiny frontal area reduces its chance of meeting a large grain, but it cannot reduce the probability to zero. Research on relativistic spacecraft suggests that gas and dust can erode, melt, implant atoms into, charge, or deflect parts of the vehicle. Thin protective layers may limit some damage. Needle-like orientation can reduce cross-sectional area. A sacrificial shield could sit in front of sensitive electronics. None of these ideas is absurd. None has been tested over a light year at 1/5 of light speed. The popular version often imagines every dust grain as a bomb and concludes that relativistic travel is instantly fatal. That is too dramatic. The opposite claim, that the medium is so empty it can be ignored, is also too easy. The real problem is statistical. Most encounters are small. A rare, larger particle can dominate the risk. Engineers must design for a distribution they cannot sample completely before launch, along a route where repair is impossible. Arrival reveals the price of all the speed. A probe traveling at 20% of light speed covers the Earth-Moon distance in about 6 seconds. It could cross a region the size of the inner solar system in hours. The camera must find, track, expose, and store images, while targets sweep through its field at extraordinary angular rates. Instruments must decide what matters without waiting for instructions. A planet may be partly hidden behind its star on the far side of its orbit, or covered in clouds during the encounter. The probe gets one pass. It also has no obvious break. The laser array is behind it, light years away. The target system contains starlight and magnetic fields, but using them to remove a velocity of 0.2 c is profoundly difficult. Concepts involving magnetic sails, electric sails, photogravitational assists, or staged reflective sails have been proposed. Some may reduce arrival speed under carefully chosen trajectories. They generally trade velocity for travel time, require enormous sail areas, depend on stellar geometry, or demand materials and control beyond current capability. Without deceleration, the probe is a camera fired through a system. That may still be scientifically transformative. A close image of a planet around another star, spectra taken from within the system, and direct measurements of the local plasma environment would be historic. A flyby is not a failure merely because it cannot stop. But it is not equivalent to arrival in the sense most people imagine. It cannot orbit, revisit a target, wait for weather to clear, deploy a lander, or build anything. Its science is compressed into a brief interval, and its hardware continues into interstellar space forever. Even the data return is not guaranteed. A gram-scale probe has a little power and a small transmitting aperture. From a light year away, its beam spreads. From Alpha Centauri, it spreads for more than 4 years before reaching us. Earth may need enormous receiving arrays and long integration times to extract a faint signal from background noise. The probe must point its transmitter toward a moving solar system with extreme precision, while its own attitude may have been disturbed by impacts or magnetic torques. This does not defeat the laser sail concept. It defines what success would mean. A successful beamed sail mission would prove that interstellar reconnaissance does not require a star-harnessing civilization. It would show that a species capable of constructing a vast optical array, manufacturing advanced sails, and coordinating global-scale energy pulses could send small instruments to nearby stars. That is a radical narrowing of the problem. It also strengthens the central claim. The first fast crossing will probably be purchased by stripping the mission down until almost everything associated with transportation has disappeared. No crew, no cargo, no return, perhaps no braking, little shielding, tiny instruments, and one short chance to observe. The light year yields when the payload becomes almost weightless. Put capability back, and the cost returns. Capability begins with mass, and mass brings us to relativity. At the speeds of Voyager or Parker Solar Probe, Newtonian mechanics is accurate enough for almost every practical calculation. Kinetic energy is approximately 1/2 of mass multiplied by velocity squared. Time passes at nearly the same rate aboard the spacecraft and on Earth. Adding speed is difficult because engines are limited, not because space-time has become visibly strange. At 10 or 20% of light speed, relativistic corrections are still modest but no longer irrelevant. At 90%, they dominate. The correct kinetic energy is not 1/2 mv squared. It is the rest mass energy multiplied by the Lorentz factor -1. As velocity approaches light speed, the Lorentz factor rises without limit. A massive object can move arbitrarily close to the speed of light in principle, but it cannot be accelerated to light speed by any finite supply of energy. This is sometimes described by saying that mass increases with velocity. Modern physics usually avoids that language. The spacecraft's invariant mass does not change merely because it moves. What rises is its energy and momentum, and therefore the resistance of the entire system to further acceleration as seen from another frame. The distinction sounds technical, but it prevents a misleading picture in which matter somehow gains substance from speed. The energy numbers reveal why the wording matters less than the consequence. Take a 1,000 kilogram probe, roughly the mass of a small car. At 10% of light speed, its kinetic energy is about 4.5 times 10 to the 17th joules. At 20%, about 1.9 times 10 to the 18th. At half the speed of light, about 1.4 times 10 to the 19th. Those are the energies stored in the motion of the payload alone. They do not include the engine, fuel, beam losses, conversion losses, radiators, shielding, or support structure. They also assume that every joule supplied by the civilization becomes useful kinetic energy, an efficiency no real propulsion system achieves. For a gram-scale sail, the energy at 20% of light speed is about 2 trillion joules. That is still enormous for a gram, which is why the laser array must deliver tremendous power. Yet it is an infrastructure problem on a recognizable planetary scale. Increase the payload from 1 gram to 1,000 kilograms, and the energy increases by a factor of 1 million. Increase it to 1 million tons, a mass that is not obviously excessive for a crude interstellar habitat with shielding and closed life support, and the kinetic energy at half light speed becomes roughly 1.4 times 10 to the 25th joules. At humanity's current rate of total energy use, accumulating that much energy would take tens of thousands of years, even before losses. A round trip requiring acceleration and deceleration at both ends multiplies the velocity changes. The mission does not literally need 4 times the same launch energy in every architecture, because external beams, staged systems, or resources at the destination can alter where the energy comes from. But no architecture erases the momentum and energy that must be exchanged. This is why comparisons based only on distance can mislead. Once a spacecraft reaches cruising speed in ideal empty space, coasting another light-year costs almost no propulsion energy. A 10 light-year journey does not automatically require 10 times the acceleration energy of a 1 light-year journey. It requires 10 times the cruise duration and roughly 10 times the exposure to failure, radiation, dust, and life support demand. The source of difficulty shifts. The energy bill is paid primarily when velocity changes. The time bill is paid while distance passes. The reliability bill is paid every second. That distinction corrects one of the most common exaggerations in interstellar arguments. 10 light-years is not simply 10 times more impossible than 1. For a flyby probe already at cruise speed, the additional distance may be mainly a problem of longevity and communication. For a crew, those additional years may require more consumables, more shielding, more repairs, and a more stable ecosystem. For a mission that must break, the destination still demands a second major exchange of energy, regardless of whether the cruise was 1 light-year or 10. Relativity also changes the experience of time, though not enough to rescue modest speed missions. At 10% of light speed, a clock aboard the ship runs only about 0.5% slower than a clock on Earth. A 10-year crossing feels almost 10 years to the crew. At 20%, the difference is about 2%. A 5-year Earth frame crossing feels only a little shorter aboard the craft. Starshot does not gain much from time dilation. At half the speed of light, shipboard time runs at about 86.5% of the Earth rate. A 2-year Earth frame crossing of 1 light-year, ignoring acceleration and braking, would feel like roughly 21 months aboard. Noticeable, but not revolutionary. At 90% of light speed, the difference becomes dramatic. Earth measures a little more than 13 months for the crossing. The travelers experience roughly 6 months. At 99%, Earth sees just over a year, while the travelers experience less than 2 months. The universe appears to offer a bargain. Go close enough to light speed, and the crew can cross enormous distances within a lifetime. In the traveler's frame, the distance along the direction of motion is length contracted. The stars seem closer. A sufficiently fast ship could traverse the galaxy while its crew aged far less than the people who remained behind. The bargain has 2 clauses that cannot be ignored. The first is energy. Time dilation becomes spectacular only where the Lorentz factor and kinetic energy are already severe. At 99% of light speed, the kinetic energy of every kilogram is a little more than 6 times the rest energy of that kilogram. For a large vessel, the requirement belongs to a scale far beyond present civilization. The second clause is separation. Time dilation shortens the traveler's experience, not Earth's history. A crew may cross a long distance while aging only a few years, but decades, centuries, or millennia can pass at home. The journey becomes a form of one-way travel through time. For a single light-year, this social effect is small unless the ship travels extremely fast. For journeys across dozens or hundreds of light-years, it becomes central. A traveler can return biologically young to a civilization that has aged beyond recognition. Their friends may be dead. Their language may have changed. The mission that seemed short aboard the ship has carried them out of their historical era. This consequence is sometimes used as evidence that relativistic travel is pointless. That conclusion goes too far. Human beings have repeatedly accepted permanent separation for exploration, migration, survival, or belief. A future society may judge the loss differently. Robotic missions do not grieve. A crew that never intended to return may see time dilation as an advantage. The stronger point is that relativity does not make distant travel free. It exchanges one kind of duration for another. The travelers save subjective time by spending energy and surrendering simultaneity with home. At high velocity, the interstellar medium also changes character. In the spacecraft frame, gas ahead is not a quiet collection of atoms. It is a particle beam. At 20% of light speed, incoming protons carry tens of mega-electron volts of kinetic energy. At 90%, the energy rises into the giga-electron volt range. Heavy nuclei produce cascades of secondary particles when they strike shielding. For a gram-scale probe, the main concern may be material erosion, charging, trajectory deflection, and electronics damage. For a crewed vessel, the concern includes radiation dose. A thick forward shield can absorb particles, but the collisions create heat and secondary radiation. The shield itself becomes activated or damaged. The required mass must be accelerated with the rest of the ship. Dust is less frequent and more violent. Its danger cannot be captured by a single dramatic comparison because grain size and abundance vary. A small grain at relativistic speed can excavate a crater or vaporize local material. A larger grain could destroy an unprotected craft. The ship may use layers separated by distance so that an impact vaporizes the first layer and spreads before reaching the next. It may project dust or plasma ahead as a sacrificial shield. It may use radar or lasers to detect larger particles, though seeing a tiny grain early enough at relativistic closing speed is itself a formidable problem. Every proposed defense costs mass, power, area, or complexity. The faster the ship moves, the more severe the impacts become, and the less time remains to respond. There may be a velocity at which adding speed reduces travel time, but increases shielding mass so sharply that the total mission becomes harder rather than easier. That optimum will depend on the vehicle. A wafer probe can accept risks a crew cannot. A fleet of 1,000 chips can tolerate a 90% loss rate if 10 return data. A single inhabited ship cannot be designed on the same logic. Speed, then, is not a universal measure of progress. It is one variable in a design that must survive its own solution. The arrival problem deserves more attention because it overturns the visual language of space travel. In most stories, the difficult moment is departure. Engines ignite, a vehicle climbs, and the destination waits passively. Real interstellar flight reverses the emphasis. Departure occurs near infrastructure. Power stations, construction yards, telescopes, navigation beacons, repair crews, and replacement parts can all exist close to the point of launch. Arrival occurs in a system where none of that may exist. A spacecraft approaching a target at 10% of light speed covers 30,000 kilometers every second. If its sensors discover an unexpected planet, dust cloud, or trajectory error, the time available to react is brutally short. A command from Earth cannot help. At a distance of 1 light-year, a message needs a year to arrive. At Alpha Centauri, more than 4 years. The spacecraft must be an autonomous scientific institution compressed into hardware. Autonomy in present space missions is limited and carefully bounded. A Mars rover can avoid a rock, choose among targets, and protect itself during faults. But human teams plan much of its activity. Deep space probes execute stored sequences and enter safe modes. When something unusual happens, engineers study telemetry, simulate options, and send new commands. An interstellar probe may not have that luxury. During a fast flyby, the entire encounter can end before Earth receives the first sign that it has begun. The machine must identify objects, update its ephemeris, prioritize observations, control exposure, protect memory, aim communications, and recover from faults without consultation. It may need to interpret a planetary system that was poorly known when it left Earth decades earlier. This is where advanced artificial intelligence could matter, but the phrase should not be used as magic. A learning system can select targets and adapt plans. It cannot repair a burned power converter unless the spacecraft carries tools, spares, access paths, and a body capable of manipulating them. Software can route around some failures. It cannot rewrite damaged silicon indefinitely. Autonomy reduces dependence on Earth. It does not abolish material decay. The braking method controls everything that happens next. A conventional rocket can turn around and fire its engine, but it must carry propellant. A fusion probe that accelerates for years may reserve comparable capability for deceleration. The initial mass then rises because the departure stage must accelerate the arrival stage and its fuel. Staging helps, but every stage adds tanks, engines, interfaces, and failure modes. A magnetic sail offers another possibility. A loop or field interacts with charged particles in the interstellar medium or stellar wind, exchanging momentum without consuming conventional propellant. In a dense, stellar wind near the destination, the effect could become stronger. Electric sails and plasma magnets explore related ideas. Their appeal is obvious. Braking medium is already present. Their limitation is equally obvious. The medium is thin. To generate meaningful drag, the effective magnetic structure may need to span enormous distances. Superconducting loops, plasma currents, or charged tethers must remain stable while the craft moves at thousands of kilometers per second. The braking distance may extend across a significant fraction of a light year. That is not disqualifying, but it means the arrival maneuver begins long before the star looks close. A photon sail may use the destination star's light. Turn the sail toward the star, pass close enough, and radiation pressure plus gravity can remove or redirect some velocity. Studies have shown that very low-mass sails might use a sequence of stellar encounters in a multiple-star system to slow into a bound trajectory. The catch is that arrival speed must be far below the 20% target usually associated with rapid starshot flybys. Slowing with starlight may stretch a 20-year journey into a century or more, and the sail area requirements can become enormous for even a small payload. This is a recurring law of mission design, though not a fundamental law of nature. The feature that solves one problem often changes the mission until the original headline no longer applies. A sail that can brake may need to travel more slowly. A fusion ship that can stop may need far more propellant. A heavily shielded crew vessel may accelerate less efficiently. A redundant system may be less vulnerable to failure, but harder to launch. The design is not a ladder on which every improvement moves upward. It is a web of trades. Suppose a future civilization chooses to send a robotic probe across 1 light-year and stop. The destination is not another star, because no star lies exactly 1 light-year from the Sun. The exercise is therefore abstract, but useful. At 10% of light speed, cruise takes about 10 years. If the craft accelerates gently and decelerates gently, total flight time is longer. If acceleration is limited to protect instruments or crew, the powered phases may consume a significant fraction of the route. At 1 Earth gravity, a ship would reach relativistic speed quickly enough that a 1 light-year mission becomes dominated by the need to reverse acceleration near the midpoint. In an ideal relativistic calculation, continuous acceleration for half the distance and continuous deceleration for the other half can make the trip comfortable for a crew. The equations are beautiful. The required power is not. Maintaining 1g acceleration for a massive ship means delivering enormous force continuously. The engine must expel momentum every second, and its energy demand rises as the ship accelerates. If the exhaust velocity is much lower than light speed, the propellant ratio becomes severe. If the exhaust is photons, the thrust per unit power is extremely low. A photon rocket produces only a few newtons of thrust per gigawatt. Lifting a large starship at 1g with pure photon thrust would require power on a scale that makes modern civilization disappear into rounding error. The elegance of constant acceleration therefore hides the engine. It is a description of motion, not a practical design. Arrival also requires knowledge of the destination. From Earth, astronomers can measure a nearby star's position and proper motion with great accuracy. Over decades, however, small uncertainties accumulate. Unknown planets, comets, dust structures, or stellar activity can alter the local hazard map. A fast probe may launch scout vehicles ahead, But those scouts must communicate their findings backward to a mothership that is following close behind at similar speed. The warning time can be short. A fleet architecture may be safer. Send many small pathfinders first. Use their data to refine later trajectories. Build a chain of communication nodes. Deliver braking infrastructure gradually. The first missions may only fly through. Later missions may deploy sails or power systems. Eventually, a vehicle may arrive to find equipment waiting. This strategy changes interstellar exploration from a heroic voyage into an accumulating infrastructure project. It resembles the development of oceanic navigation, railways, or planetary spaceflight more than a single leap. Routes become safer because previous missions leave knowledge and hardware behind. The strongest objection is powerful. Perhaps no giant crewed starship needs to solve every problem at once. Robotic systems could prepare the destination. Self-repairing machines could build receivers, beacons, or fuel factories from local materials. A small seed payload could matter more than a large finished ship. That is possible in principle, but it moves the challenge into robotics, computation, and reliability. A machine that can land in an unknown system, mine resources, refine materials, manufacture complex parts, and reproduce a technological base is not a simple probe. It is an automated industrial ecology. Its mass may be far smaller than a city, yet its functional complexity may be comparable to one. Again, the distance is not the sole barrier. The requirement is preserved capability. If a 1-gram camera can cross quickly, matter has crossed. If a 100-ton factory can cross, stop, and build, civilization has extended itself. Those achievements share a unit of distance and almost nothing else. For human travel, preserved capability begins with an organism that did not evolve for the journey. The human body is adapted to Earth's gravity, atmosphere, magnetic environment, day-night cycle, microbial ecology, and social world. A starship must reproduce enough of those conditions to keep people alive and mentally functional. Every substitute becomes machinery. Every machine can fail. Microgravity causes bone loss, muscle atrophy, fluid shifts, and changes in vision and immunity. A journey lasting years may require artificial gravity, perhaps by rotating part of the habitat. Rotation introduces bearings, seals, structural loads, and moving interfaces, unless the entire craft spins. A small rotating habitat creates noticeable Coriolis effects. A larger one is more comfortable and more massive. Radiation outside Earth's protective magnetosphere is another constraint. Galactic cosmic rays contain high-energy nuclei that penetrate shielding and produce secondary particles. Solar storms can deliver intense doses over short periods. A fast interstellar vessel adds the forward particle flux created by its own motion through the interstellar medium. Hydrogen-rich materials such as water or polyethylene can be useful against some radiation because they contain light nuclei. Conveniently, a crew already needs water. Tanks can be arranged around living areas as shielding, yet water has mass, and a closed system never recycles perfectly. Pumps fail. Filters clog. Microbes evolve inside plumbing. Trace contaminants accumulate. A life support system intended to run for decades must be repairable at a level far beyond replacing modules. The International Space Station demonstrates both the promise and the problem. It recycles water, controls atmosphere, and supports people for long periods. It also receives regular cargo, replacement parts, software support, and the attention of large teams on Earth. Its orbit allows evacuation within hours. An interstellar habitat would have none of those margins. Food can be stored for a limited mission, but long voyages favor biological production. Crops convert light, carbon dioxide, water, and nutrients into food and oxygen. They also introduce pests, disease, genetic drift, pollination requirements, waste streams, and ecological feedback. A stable closed ecosystem is not merely a garden in space. It is a coupled chemical and biological network in which small imbalances can grow slowly for years before becoming lethal. This is one reason a crewed mission cannot be reduced to the kinetic energy of its dry mass. The ship must carry time in physical form, spare components, nutrients, medical options, genetic diversity, diagnostic tools, and the capacity to respond to events no design team predicted. Reliability calculations become unforgiving over long durations. If a component has a small probability of failure each year, the chance that it survives unchanged for a century may be poor. Redundancy helps until common causes defeat all copies. Identical pumps may share the same manufacturing flaw. A radiation event may damage every unshielded controller. A software error may propagate across a redundant network. A robust starship needs diversity as well as duplication. Different methods must be able to perform the same essential function. Mechanical controls may back up electronics. Biological oxygen production may back up chemical scrubbers. Additive manufacturing may produce parts from stored feedstock. Machine tools may repair the printers that make other parts. The crew may need the knowledge of engineers, physicians, farmers, chemists, programmers, and machinists. At that point, the vehicle is no longer transporting passengers. It is transporting a miniature technological society. There is a counter-argument. A 1 light-year journey at 20% of light speed lasts only 5 years in Earth's frame, so it does not require generations, forests, or a self-sufficient civilization. A well-supplied habitat could carry consumables and redundancy much as a submarine or polar station does. That is true. 1 light-year is not Alpha Centauri, and a 5-year trip is not a century. But reaching 20% of light speed with a crewed habitat is exactly where the mass and energy problem becomes extreme. The architectures that make 5 years plausible are optimized for grams. The architectures that can push large payloads, such as speculative fusion or nuclear pulse vehicles, more often yield speeds of a few percent to perhaps around 10% under optimistic assumptions. At 5%, 1 light-year takes 20 years before acceleration and braking. At 1%, a century. The mission cannot choose its travel duration independently of the propulsion system and payload. Fast travel reduces life support time while demanding more energy, shielding, and acceleration capability. Slow travel reduces propulsion severity while requiring a more durable society in miniature. There is no setting that makes all variables small. Suspended animation is often inserted at this point. If the crew could sleep without aging or consuming much, life support would shrink. No demonstrated technology can place healthy humans into years of reversible metabolic suspension. Medical hypothermia can slow metabolism for limited periods. Some organisms tolerate cryptobiosis. Neither fact establishes a path to freezing or hibernating an adult human for decades without severe damage. Generation ships avoid extreme speed by allowing people to live and reproduce during the voyage. They are physically compatible with known laws, which is not the same as being near-term engineering. A generation ship must maintain a viable population, culture, economy, educational system, and ecosystem for centuries. Its inhabitants do not merely crew a mission. They are born inside a project they did not choose, and many will die before the destination is reached. The ethical challenge is as real as the technical one. Who decides the ship's laws? How are resources allocated? What happens if a later generation rejects the mission? Can a society remain free when its habitat has strict physical limits and failure threatens everyone? The stars do not answer these questions. They become part of the propulsion system because social stability is required to keep the vehicle operating. Embryo missions are sometimes proposed as a lighter alternative. Frozen embryos or genetic material would travel with robotic caretakers, and human beings would be born after arrival. This reduces habitat mass during cruise, but requires machines able to gestate, raise, educate, and protect children without an existing human society. It replaces one difficult system with a more morally and technically demanding one. Digital minds or uploaded consciousness are an even more radical possibility. If a human identity could be instantiated in computation, the payload might shrink and tolerate acceleration. At present, this belongs to speculation. Neuroscience does not know how to copy a person's complete mental state, and philosophy has no consensus that a copy would preserve personal continuity. It may someday become relevant. It cannot be used to make today's starship calculations easy. A more credible path begins with robots. Machines already tolerate vacuum, long isolation, and accelerations humans cannot. Future probes may repair themselves, cooperate as swarms, and make scientific decisions. They may be the first entities from Earth to cross 1 light-year quickly and do useful work. Some people hear that conclusion as a defeat, as though exploration only counts when a human face looks through a window. That standard is historically narrow. Most of what humanity knows about the outer planets came from robotic spacecraft. No person has visited Jupiter, Saturn, Uranus, Neptune, Pluto, an asteroid, or a comet. Yet those worlds have entered human understanding through instruments. An interstellar probe doesn't need to carry a human body to extend human perception. The strongest case for optimism therefore rests on separating exploration from migration. Exploration can begin with tiny probes and become progressively more capable. Migration demands transport of life, industry, and autonomy at a scale that transforms the problem. This separation also explains why arguments about a single light-year often generate confusion. One speaker imagines a chip taking photographs. Another imagines a crew arriving in orbit around a habitable planet. Both use the phrase interstellar travel. They are debating different machines. Once the mission is named precisely, the apparent contradiction dissolves. Fast interstellar probes are not obviously forbidden. Fast interstellar human transport remains far beyond demonstrated capability. Slow human transport may be allowed by physics, but demands closed systems and social continuity we have never achieved. None of these statements proves what will be possible in 1,000 years. They describe the pressure each architecture must face. There is still one propulsion idea that seems to erase the energy density problem entirely: antimatter. When matter and antimatter meet, their rest mass can be converted into other forms of energy. No chemical reaction, fission process, or fusion reaction offers a greater theoretical energy density. In a rocket equation dominated by exhaust velocity, antimatter seems almost designed for interstellar flight. The word theoretical carries most of the weight. Antimatter is produced routinely in particle physics, but in microscopic quantities. It is not mined from a convenient reservoir. Creating it requires first supplying energy to accelerators, and present production is fantastically inefficient. The total amount ever manufactured is tiny compared with even a speck of dust. A starship might require milligrams, grams, or far more, depending on whether antimatter supplies all propulsion energy or merely triggers fusion reactions. Storage is harder than production in a different way. Antimatter cannot rest against the wall of an ordinary tank. Charged antiparticles can be suspended in electromagnetic traps under extreme vacuum. Neutral antimatter is even more difficult to confine. Laboratory traps hold small numbers of particles for research, not industrial quantities for decades aboard a vibrating, accelerating vehicle. An antimatter engine must also convert annihilation products into directed momentum. Some energy emerges in particles that are difficult to reflect or collimate. Neutrinos escape. Gamma rays penetrate materials and create heat and radiation. A fuel with perfect mass-to-energy conversion does not automatically produce a perfect rocket. Antimatter therefore illustrates a broader lesson. Energy density is not the same as usable propulsion. The complete chain matters: production, storage, controlled release, conversion to exhaust, heat rejection, shielding, and failure containment. A containment fault involving a starship-scale inventory would not resemble a leaking fuel tank. The Bussard ramjet attacks the problem from the opposite direction. Instead of carrying fuel, a craft would use a vast magnetic field to collect hydrogen from the interstellar medium and fuse it. The faster the ship moves, the more material sweeps through its collector. In the original vision, continuous acceleration could carry the craft toward relativistic speed without an enormous onboard propellant supply. The appeal is so strong that the ramjet became a symbol of hard science fiction. Later analysis found that the interstellar medium is too sparse and ordinary proton-proton fusion too difficult. Collecting and compressing the particles produces drag. The magnetic field must redirect incoming matter that already has enormous momentum in the ship's frame. Under realistic assumptions, the drag may equal or exceed the thrust. Modified concepts use carried fuel and the magnetic scoop as a source of reaction mass or as a brake. But the simple image of drinking hydrogen from space and accelerating forever does not survive intact. The ramjet is valuable because its failure mode points to the same neglected variable as the rest of the story. The environment is not merely fuel waiting to be collected. At high relative speed, collecting it costs momentum. Then come proposals that do not move through space conventionally at all: wormholes, warp metrics, shortcuts created by the geometry of space-time. General relativity permits mathematical solutions with surprising properties. A traversable wormhole could connect distant regions. A warp geometry could contract space in front of a vessel and expand it behind. These ideas deserve neither ridicule nor promotion as available technology. Mathematical permission is not engineering feasibility. Many versions require negative energy densities or exotic stress energy configurations not known to exist in useful forms. Quantum field theory allows local effects that can be described as negative energy under restricted conditions, but nothing close to the stable macroscopic structures imagined for transport. Questions of formation, stability, causality, control, and radiation remain unresolved. A future theory of quantum gravity may change the discussion. It may also confirm that useful shortcuts are impossible. At present, warp drives and traversable wormholes are research questions, not propulsion options that can be placed beside rockets and sails as though only funding separates them. This boundary is important for scientific caution. Declaring all exotic travel forever impossible would exceed the evidence. Treating a solution to Einstein's equations as a blueprint would also exceed it. The honest position is narrower. Known, experimentally supported methods for moving useful mass across a light year must pay in energy, momentum, time, and reliability. No demonstrated loophole removes those costs. That sentence leaves room for discovery without using discovery as an excuse to ignore present physics. Technological optimists offer a serious challenge here. History is filled with confident limits that later collapsed. Heavier-than-air flight, controlled nuclear reactions, landing rockets, detecting gravitational waves, and imaging a black hole all seemed unreachable before the necessary theory, materials, and instruments matured. Why assume interstellar engineering will be different? The challenge is valid. Predictions made from current technology are fragile. A laser array that seems extravagant today may become ordinary after centuries of growth. Materials may acquire combinations of strength, reflectivity, thermal performance, and self-repair we cannot manufacture now. Fusion may become a mature energy source. Automation may reduce payload mass by orders of magnitude. A civilization with large industries in space will not price missions the way a planet-bound civilization does. The correct answer is not that progress will stop. It is that physical scaling is different from technological ignorance. Before aircraft, people lacked an engineered way to produce lift and control. Nothing in physics required infinite energy for flight. Once engines, airfoils, and materials crossed a threshold, performance improved quickly. Relativistic travel contains similar engineering thresholds, but it also contains invariant constraints. Momentum must be exchanged. Waste heat must leave. Signals cannot outrun light. A massive craft cannot be accelerated to light speed with finite energy. These are not gaps waiting for a better alloy. Breakthroughs can change coefficients by enormous factors. They can lower mass, raise efficiency, improve exhaust velocity, and move infrastructure off the vehicle. They can change which mission is practical. They cannot simply declare the equations irrelevant. This is why the strongest position is neither pessimism nor faith. It is conditional optimism. A tiny probe crossing 1 light-year in years appears compatible with known physics, although the engineering remains formidable. A large robotic probe that can stop may require fusion, advanced sails, or infrastructure at both ends. A crewed vessel traveling within a human lifetime requires energy and systems far beyond anything demonstrated. A ship carrying a self-sufficient population asks not only for propulsion, but for a stable artificial world. Each step is possible in a different sense. Possible can mean not prohibited by a known law. It can mean a credible concept has been published. It can mean components exist in laboratories. It can mean an integrated prototype has worked. It can mean a society can afford and operate the system. Confusing these meanings creates both false hope and false despair. Project Daedalus is physically reasoned but unbuilt. Nerva hardware was tested, but it is not an interstellar engine. Fusion ignition has been achieved at a target, but not as a power plant or rocket. Photon pressure is routine physics, while a 100-gigawatt coherent beamer is not routine engineering. Voyager is operational reality, while its light-year travel time belongs to geological history. The argument becomes clearer when every claim is placed on that ladder. We know how far 1 light-year is. We know the speed of light exactly by definition. We know the rocket equation. We have measured relativistic energy and time dilation in particles and clocks. We have flown solar sails and electric thrusters. We have built nuclear rocket reactors and produced fusion ignition in laboratories. We do not know whether a meter-scale sail can survive the full starshot acceleration environment. We do not know how to operate a fusion pulse engine for years. We do not know how to store macroscopic antimatter. We do not know how to keep a closed human ecosystem healthy for generations. We do not know whether future societies will choose to build the infrastructure even if they can. The unknowns are not all of the same kind. Some are engineering programs. Some are economic choices. Some are biological uncertainties. Some are open questions in fundamental physics. Treating them as one vague obstacle called distance hides, where progress could actually occur. The temptation is to turn those unknowns into a story about the destiny of civilizations. The Kardashev scale classifies hypothetical societies by the amount of power they can use: planetary, stellar, or galactic. It is a useful thought experiment because interstellar propulsion is inseparable from energy infrastructure. A society collecting a significant fraction of its star's output would regard energy budgets that overwhelm us very differently. But the scale is not a law of evolution. Civilizations do not have to climb it in a fixed sequence. Greater intelligence does not guarantee greater power consumption. Advanced technology may become more efficient, more compact, or less expansionist. A society could send sophisticated probes through extreme miniaturization without surrounding its star with collectors. Another could command enormous energy and choose not to travel. Calling 1 light-year a civilizational filter is therefore a metaphor, not a scientific result. The metaphor still reveals something useful. Interstellar projects require the coordination of energy, industry, and time. Present humanity uses power on the order of tens of terawatts. We launch spacecraft with masses of tons and assemble structures in orbit with masses of hundreds of tons. A serious crewed interstellar vehicle might require millions of tons, power systems far beyond the global grid, and construction in space rather than launch from Earth's surface. That gap is not bridged by a single engine breakthrough. It requires an industrial environment in which large masses can be obtained, processed, assembled, and tested beyond Earth. Asteroids may supply metals. The Moon may supply some materials and a lower gravity construction base. Solar collectors built in space may provide power without passing through the atmosphere. None of this makes a starship inevitable. It changes the starting point. A civilization with mature solar system industry could attempt missions that are nonsensical for a civilization trying to launch every component from Earth's surface. The most important development for interstellar travel may therefore be a technology that never leaves the solar system. Cheap access to orbit, autonomous mining, high-temperature materials, closed-loop life support, fusion power, or large-scale manufacturing in vacuum. This is less dramatic than a warp drive. It is also how difficult capabilities usually emerge. The final vehicle rests on layers of infrastructure built for other purposes. There is another counter-argument to the civilizational scale view. Time can substitute for power. A society does not need to push a ship to 10% of light speed if it accepts a journey of centuries. A slow probe can be launched with smaller energy investment. A generation ship can trade velocity for habitat longevity. A fleet can spread launches across decades. The light year may be crossed by patience rather than by stellar power. That is true in the energy ledger and harsh in the reliability ledger. At Voyager speed, a 1 light-year mission lasts longer than recorded human history. At 1% of light speed, it lasts a century. A century is not absurd for an institution, but it is severe for a machine and transformative for a crew. The slower route reduces kinetic energy and collision severity. It increases exposure to cosmic radiation, component aging, ecological drift, social change, and loss of support from home. Time is not a free substitute. It is another resource the spacecraft must carry. Long duration also changes the reason to send the mission. A probe launched today at 1% of light speed would cross 1 light-year around the early 22nd century. A later civilization might develop a faster vehicle and overtake it. This is sometimes called the weight calculation. Launching immediately is not always the quickest way to receive results if propulsion improves rapidly. The calculation cannot tell a society exactly when to launch because future progress is uncertain. Waiting forever guarantees no mission. Launching crude pathfinders may teach the technologies that faster missions require. Early probes can map dust, test communications, and demonstrate long-lived systems even if later craft pass them. Interstellar progress may look less like one decisive departure and more like overlapping waves. Slow, durable probes leave first. Faster sails follow. Larger vehicles arrive later. Communication relays and braking systems accumulate. The route becomes a history rather than a line. The 1 light-year threshold then acquires a different meaning. It is not an entrance examination that a civilization passes once. It is a sequence of increasingly demanding definitions of reach. The first definition is physical. Did a human-made object cross the distance? The second is informational. Did it observe something and return data? The third is operational. Did it arrive with enough control to remain in the destination system? The fourth is industrial. Could it repair itself, build, or prepare the way for later missions? The fifth is biological. Could living humans arrive healthy? The sixth is civilizational. Could a community persist, reproduce, and remain capable after separation from Earth? A gram-scale sail may satisfy the first two. A fusion probe with braking might satisfy the third. An autonomous seed factory would attempt the fourth. A crewed ship would confront the fifth. A settlement vessel would need all six. When these goals are collapsed into one phrase, debates become theatrical. One side says the stars are impossible because a city cannot be accelerated with today's energy. The other says they are near because a chip can be pushed by light. Each side selects a true statement and attaches it to the wrong definition of travel. The more honest stance is uncomfortable because it denies both emotional satisfactions. The distance is not an absolute prison. That weakens the grand pessimistic claim that humanity is forever confined to the solar system. The distance is also not merely a large engineering project waiting for a better rocket. That weakens the easy optimism that historical progress guarantees a human voyage. Known physics leaves a narrow opening. Through it, tiny probes may pass first. Larger missions must pay for every added function. There is no shame in that sequence. Astronomy itself began with photons crossing distance while matter remained home. Every telescope is a machine for receiving messages from places we cannot visit. An interstellar probe reverses the direction. It sends our instruments into the message. 1 light-year also imposes a communication reality that cannot be engineered away. At the far end, a signal needs 1 year to return. A question and answer require at least 2. The distance creates separate decision worlds. Earth cannot supervise events in real time, and the probe cannot know Earth's present condition. For a human crew, that delay changes family and society even without strong relativistic time dilation. A message sent at departure may receive a reply years later when context has shifted. Emergencies are private. Decisions become local. An interstellar community would not be a remote branch controlled continuously from Earth. Light speed grants it autonomy whether politics intends to or not. That autonomy may be one of the deepest consequences of crossing. The propulsion system moves matter, but the communication delay moves authority. A settlement beyond even a few light years would share ancestry with Earth, not a common present. The original fear, inspired by 1 light-year, is therefore partly justified, but for the wrong reason. The number is not terrifying because 9.46 trillion kilometers is too large for nature to permit. Nature crosses it constantly with light, particles, dust, and stars. The number is terrifying because it exposes how many assumptions about travel depend on Earth being near. Near enough to send help, near enough to replace a part, near enough to wait for instructions, near enough for the people at home and the people aboard to inhabit the same unfolding events. Beyond that, a vehicle must become more complete. The farther and faster it travels, the less it can borrow from the world that launched it. This is why the decisive technology may not be the engine. It may be the ability to build systems that remain useful without rescue. Consider what a credible first campaign might look like if no miraculous physics appears. It would probably begin inside the solar system. Small laser sails would be tested over lunar and planetary distances, where their trajectories could be measured and failures recovered quickly. Materials would be exposed to intense beams for seconds, then minutes. Arrays would learn to hold phase through atmospheric turbulence or be moved into space. Tiny spacecraft would prove that they can navigate, store energy, and point a weak communication beam across billions of kilometers. The first targets might not be stars. Probes could race toward the outer heliosphere, the solar gravitational lens region, or distant objects in the Oort cloud. These missions would still be historic. They would test high-speed impact survival, autonomous science, and decades-long data links without demanding a full interstellar crossing. Later, swarms could be launched toward a point 1 light-year away simply because the distance itself is useful. There is no star there, but the probes could measure the interstellar medium, map magnetic fields, count dust impacts, and return information about the path future missions would follow. Some would fail. Others would become the first human artifacts to place a full light-year between themselves and the Sun on a timescale measured in years rather than millennia. That achievement would not look like a starship arriving over an alien ocean. It might look like a faint sequence of bits detected by a huge receiver after a decade of silence. Yet the meaning would be enormous. It would show that the fast probe side of the argument is no longer theoretical. The next stage would ask for more than survival. Could a probe carry a larger telescope? Could several sails combine observations? Could one vehicle release sub-probes before a flyby? Could a forward shield endure the measured dust environment? Could a laser communication system return useful data from 4 light-years? Could navigation remain accurate enough to pass close to a planet whose orbit was refined after launch? Each answer would move the boundary from physics toward operations. Only after those steps would braking become the dominant experiment. A mission might travel more slowly so it could use a target star's radiation. It might carry a magnetic sail. It might arrive in a system where earlier probes had deployed a beacon or reflector. The first successful deceleration would matter more than another speed record because it would convert passage into presence. This sequence offers a rebuttal to the claim that interstellar travel requires a civilization to solve everything before beginning. It does not. A civilization can learn in increments. The first light year can be crossed by a machine that does almost nothing. The next can be crossed by a machine that observes. Later, machines can maneuver, stop, and build. But incremental progress does not guarantee the final human step. There may be ceilings created by biology, economics, risk tolerance, or choices rather than by equations. A society may decide that robotic presence is enough. It may explore thousands of systems through instruments while people remain close to their star. That would still be an interstellar civilization in an informational sense, even if no human body crosses the void. The definition matters because it changes what success looks like. If success means planting a flag on a planet around another star, the first light year remains almost useless. The nearest stellar system is more than 4 times farther. A crew must survive not one crossing, but several, and it must reach a specific moving target. If success means extending human observation and agency beyond the solar system, the threshold is nearer. There is also a danger in letting the drama of distance overshadow the value of the solar system itself. The space between Earth and Neptune contains enough challenge, material, and scientific mystery for centuries of exploration. Building the infrastructure that might someday support interstellar flight would transform our relationship with the Moon, asteroids, Mars, and the outer planets long before any probe reached another star. A large orbital industry, reliable closed-loop habitats, high-power propulsion, autonomous construction, and advanced radiation protection are not technologies useful only for a distant dream. They would alter life and exploration close to home. The path to 1 light-year may be built without 1 light-year being the immediate goal. This weakens another popular assumption: that interstellar ambition is meaningful only if a mission arrives soon. Civilizations routinely build capacities whose later uses were not fully understood. Navigation, metallurgy, electricity, computing, and rocketry were not developed for a single final destination. A star probe may emerge from a mature space economy rather than create one. Still, the energy scale cannot be romanticized away. Even a mature solar system civilization must choose how much power, material, and risk to devote to a payload that will disappear for decades. The receiving generation may not be the launching generation. Political credit, commercial return, and personal memory all work against projects with delayed rewards. This is where the light year tests culture as much as machinery. Not because a species must unite under one plan for 10,000 years, as dramatic accounts sometimes claim, but because someone must maintain purpose across long intervals. Antennas must still be listening. Data formats must still be understood. The mission's history must survive budget cycles, institutional reorganizations, and changing priorities. Voyager already gives a small demonstration. Its team has kept communicating with hardware launched in the 1970s, using ingenuity to manage declining power and aging systems. That continuity spans human careers, not civilizations. An interstellar program would extend the same obligation across generations. There is no physical constant for commitment. No equation predicts whether a future society will continue listening. That uncertainty should not be disguised as a solution to the Fermi paradox. The silence of the sky may involve the rarity of life, the rarity of intelligence, short technological lifetimes, communication methods we do not recognize, vast separation, or many other possibilities. The difficulty of interstellar travel is relevant, but it does not prove that civilizations remain trapped, collapse, or choose isolation. We have one technological species available for study, and it has been capable of radio astronomy for barely a century. What the light year does show is that casual expectations of visitation are poorly calibrated. Even a society much more advanced than ours would face choices about payload, speed, braking, and energy. A galaxy can contain many intelligent worlds without making physical meetings frequent. Information may travel more often than bodies. Probes may be small, rare, difficult to detect, or designed for observation rather than announcement. That conclusion is less cinematic than fleets crossing the galaxy, and more scientifically useful. It connects the silence not to a single dramatic filter, but to the ordinary multiplication of hard constraints. Distance delays communication. Speed raises energy and collision costs. Mass amplifies propulsion demands. Braking repeats them. Life adds shielding, ecology, and ethics. Reliability turns years into an engineering material. None of these alone forbids the journey. Together they determine what kind of journey survives. Return now to the two spacecraft that left together. The Voyager-like probe moves outward with patient certainty. Civilizations could rise and disappear before it crosses 1 light-year. Its slowness protects it from relativistic dust impacts and extreme energy demands, but exposes it to time. The laser sail vanishes almost immediately, driven to 1/5 of light speed by a beam brighter than any propulsion system ever built. It crosses the distance in 5 years, but purchases that speed by becoming fragile, tiny, difficult to aim, difficult to hear, and almost impossible to stop. Neither machine proves the other foolish. They occupy different answers to the same equation of purpose. Between them lies the design space of interstellar travel, nuclear pulse ships, fusion probes, magnetic sails, autonomous factories, generation habitats, and concepts not yet imagined. Some will fail because the engineering is too severe. Some will fail because their assumptions were wrong. Some may work only after the solar system has become an industrial landscape. A few may surprise us by becoming practical sooner than expected. The one conclusion that survives is not that the stars are forbidden, and not that they are waiting within easy reach. It is that the phrase reaching the stars must be earned. Crossing a line in space is one achievement. Returning information is another. Slowing down is another. Remaining alive is another. Building a second home is another. Every added verb carries mass, energy, time, and risk. 1 light-year is therefore neither a wall nor a promise. It is a scale on which our definitions are weighed. For light, it is 1 year. For Voyager, it is roughly 18 millennia. For a proposed gram-scale laser sail, it may be 5 years. For a fusion probe that can also stop, the answer is uncertain. For a human settlement ship, No honest timetable exists. Those statements can all be true because distance is only one term in the mission. The deepest barrier is not the vacuum between the stars. It is the demand that whatever enters that vacuum must carry enough of its purpose to the other side. We have already learned how to send light across it. We may learn how to send cameras. Later, perhaps, machines capable of staying. Human beings would come only after the vehicle had become more than a vehicle. A shield, a power station, a workshop, a hospital, an ecosystem, and a society. That is not a reason to abandon the dream. It is a reason to describe it accurately. The first light year will not be conquered in a single heroic leap. It will be separated into smaller problems, tested close to home, and crossed by increasingly capable machines. The wall will not fall because someone ignores physics. It will narrow because each generation learns which part of the mission can be made lighter, safer, more autonomous, or less dependent on rescue. And when the first useful signal returns from beyond 1 light-year, the achievement will not mean that distance has lost its power. It will mean that, for one small machine, purpose survived the crossing.